Good.
I think we're good. All right. Yeah, so I'm Krish. I'm the person you've been emailing. I'm the dynamics and recovery lead. We're going to all introduce ourselves.
I'm Arnav. I'm the structures lead and chief engineer.
Cool.
I'm Schooner. I'm the propulsion lead.
And I'm Dario, and I'm the avionics lead.
Great.
And then our flight record, Sam is also here, obviously.
Yep.
All right. What would you like to know about?
Quickly, so were you guys have you guys flown previously at Spaceport?
Yeah, at Spaceport. Yeah. We've been flying since 2017.
Okay, good.
Yeah.
There's a lot of stuff on the
we've been at
checklist.
2019. Yeah.
Great. There's a lot of stuff on the checklist where I'm like, oh yeah, it's really hot. Do this, don't do that.
Yeah,
but
no.
You guys have
Also,
been there, so
all three of us
Cool.
have also been to the last two Spaceport competitions ourselves personally.
Okay.
As leads. So yeah.
cool. So I don't have to go over all that stuff.
Yeah.
Why don't you just walk me through the structure of your rocket, recovery, all that kind of stuff?
Okay. Here, I'll start with recovery. You want to start with structure first?
Yeah.
All right. Let's do structure.
All right. So we're gonna work our way from bottom to top. So
Okay.
here we have our lower section.
Oh. Okay.
Here we have our lower section. It's three swept fins that are mechanically locked in a fin can design. You can kind of see if you look up there.
Yep.
There are three centering rings that are all kind of held together with these aluminum bars that go down the root cord of the fin. So that means that when these are locked into the aluminum bars, this entire fin can joint is completely rock solid without the need of any epoxy.
Is that carbon fiber?
Yeah, so we have these are actually carbon fiber Nomex composite sandwich construction. So you have hollow Nomex sections in here, and then you have solid leading and trailing edges of carbon fiber, which we're going to chamfer as well.
Great.
So yeah, we're gonna epoxy joint together all the internal faces, as well as do big epoxy fills on the outside. We just haven't gotten around to it yet. Apart from that, that is attached to our thrust bulkhead, which is sitting right here. I'll show you from the top side.
Here, we can switch to the phone too if you want.
So I don't know if you can see really well, but
I can actually.
yeah,
That works.
that aluminum bulkhead right there is CNC machined out of 6061 aluminum. It's 3/8 inch thick. We did weight relieving cuts while maintaining like 90% of the strength. We did FEA models as well as an actual compression test to see if that's true. The epoxy that's holding it is sitting in somewhat of a channel. You can grab my, yeah, thank you. So there's a channel that's been CNC cut into one of the bulkheads, and that's increased surface area a lot more. So it's gonna have a lot of strength. In our actual tests, we found that it took 9,000 newtons of force around to actually punch that bulkhead out. And our flight loads are closer to 2,000-ish. So it's well within tolerance.
Yeah, that looks pretty well built.
Both the thrust bulkhead up top as well as the lower center ring on the bottom are both thrust transfer points. So we're evenly distributing load between those as well. Yeah. So this is an example of a bulkhead. This is just a test piece we made, but you can see that kind of channel on top and bottom.
Yeah. Okay.
Yep. Any questions about lower section?
Nope.
Okay. So we'll move on to middle section. So middle section is holding both the parachute as well as the recovery system. So the two Raptors as well as our payload. So I'll flip it like this. So the bottom side has those two Raptors that you can see, the U-bolt as well. Same kind of idea for the construction of the bulkhead. It's aluminum, 3/8 inch. It's been weight relieved. We're using a 3/8 inch thick steel U-bolt, and that has lock nuts as well. So we're going to Loctite it as well as lock nut it, just so there's absolutely no chance of it coming off in flight. Apart from the two Raptors and the U-bolt, we actually also have I can't call it a churtle. What is it called? It's not the churtle.
DIN connector.
We have a DIN connector, which allows us to to plug in one cable from the avionics side, and it goes through the bulkhead and comes out on the other side and terminates in just leads that we're going to stick into both the Raptors as well as our line cutters for our parachutes.
Okay.
So you're going to transition to parachute before you go.
Yeah,
Let's go.
yeah.
This is a good transition point, I guess. So for the parachutes, we've been making our own parachutes, SRAD, since I believe 2019. So again, this year, I have like this nice subscale model for you right here. I can show you maybe a nicer picture, but it's a parachute, right? It's an elliptical parachute. It's 16 gores, made out of ultra low porosity ripstop nylon. we did experimental testing for the coefficient of drag. We found it to be about like 1.2. And this year we're doing a reefing design, so that's the big thing you want to know, I presume. So for our drogue, there's going to, if I kind of show you on here, actually, there's a bit of a like little kind of, channel at the bottom here.
Yes, yep,
For us to feed our reefing line through. That's going to be connected through to line cutters. We got the Piranha line cutters from Tinner Rocketry. And that's what's going to actually unreef the parachutes and have it go to, unfurl to the main descent rate. We did testing on our reefing rates as well. We found the experimental kind of like fit for reefing and had that lower descent rate. So we're going to doing around 40%, restricting the circumference around 40% as usual circumference for the drogue stage. And then the wire itself, I can show you the entire system if you want, but the wire goes down from the line cutter. There's a pouch that holds line cutters. They're made out of Nomex flame blanket material. And it goes down to the shroud line, which is it's all taped together on the shroud line and all that kind of fun stuff. It's slightly longer so it doesn't get in tension. And then it goes through, we use tubular 1-inch nylon for our shock cords. So it's going through the shock cord all the way to, the circle and the bay itself.
okay, so to prevent things from getting tangled up or twisted.
Yeah, exactly.
Great.
Yeah, it's well protected. Yeah. I don't know if you've our recovery system, our separation is the CO2 Raptor from Tinner Rocketry. We did the same thing last year. We had a CO2 test. It was successful. 45
Okay, so no black powder, so you don't have to worry
No
about
black powder at
cooking
all.
your
Nope.
shoots.
Nope, nothing at all. So it's one
Great.
separation, again, the line cutter is minimal. There's also Nomex around the pouch too, all that kind of fun stuff. There's absolutely no flame concern at all. Yeah.
Great.
Any other questions about recovery before we move on to the rest of the stuff?
Any concerns or thought put into the bridle rubbing against the edge of your tubes, or a zipper situation, that kind of a thing?
No. We should be fine. We also have these Nomex kind of flame blanket sleeves that we use, and we attach that around where it would kind of, going against the edge. So
Mhm.
we've had I think we had that issue back in like 2018 or something, and since then we've been pretty good about making sure that doesn't occur again.
Great.
Yeah,
Okay.
yeah.
So as long as you guys are thinking about that failure
yeah.
mode.
Yeah, that was a failure mode back in 2018, so we've been very cognizant about it. Yeah.
Excellent.
All right, rest of the story.
I'm gonna switch to this camera.
Sure.
If
You
you
want
want.
Arnav Dario to record? Yeah, I'll pin it. You want to turn it on? I don't see anything yet. Is the camera
I see mobile camera.
Oh, there we go. Yeah.
There we go. All right, awesome. So now we have the payload section. So this is the top-down view. So we can see once again those two Raptors on the side, the DIN connector that's going to be going up to our avionics bay. On the side here, you see two steel rails that are going to be holding our payload. These steel rails have obviously flat edges on the bottom. They've been fit to the body tube surface by the use of these aluminum brackets we're calling curve adapters. So those have, we have 3 curve adapters per side, and each curve adapter, if you want to see on the side, has 4 18/8 stainless steel screws.
Nice.
The hand calculations for shear, we had something like a 34 safety factor.
absurd.
It was crazy. So we're not concerned about that kind of ripping out. But
Great.
yeah, these rails correspond to 2 carriages on the side of our payload, which allow this entire thing. I was going to say seamlessly, but
Yeah, getting everything lined up sometimes.
there we go.
Nice.
Seamlessly, first try, slide it. So that is securely held on the bottom by a retention screw. And then on the top side, we're going to have cotter pins that are kind of pinning this thing in place. So in flight, there's no chance of it vibrating out. It's already a nice and tight fit, but we're going to have screws there as well to ensure that nothing comes out.
Great.
All right, any questions about middle section, payload, parachute?
What are you guys doing in your payload?
You want to talk about that?
I can. Yeah, Dario, go for it. Actually.
Yeah, so for our payload, we're gonna make a scenic interferometer. So what that basically means is on our flight computers already, we have little MEMS devices that are gyroscopes. But by using a scenic interferometer, we can make an optical gyroscope with 0 moving parts whatsoever that is completely resistant to any kind of noise. And we can get multiple magnitudes of precision greater than using a MEMS device. So the payload is currently going to kind of house that system, where we're going to kind of wind about 300 meters of optical fiber around a spool that we're going to mount in here. We're going to grab some of the pieces, and we can do some other optic circuitry that we're currently working with a physics lab here to do.
Yeah.
And that will allow us to be able to measure the rotation of our rocket real time which will really be able to help us.
We're basically using
visualization.
infrared light interference to measure the rotation of the rocket. So this
Oh,
is
that's cool.
we made a little polarization modulator. Actually, just it basically just controls kind of like the polarization of the lights. And we made that in house, which is super cool. It's like a little thingamajiggy. You know, the fiber exists somewhere over there. You have to I can go get it if you want. But
Yeah, no, that's fine.
yeah, but that's what we're doing this year. It's gonna be non-deployable. It's gonna be all in there. It's just gonna, you know, be a really effective gyroscope, basically.
That's cool. All right.
It has its own avionics boards and batteries on board, so it's going to be completely independent from our avionics bay. So it's not going to interfere with that at all. At all.
And did you guys get the have you seen the battery? They had a new thing they sent out this year where, you know,
yeah.
certain types of batteries not allowed and all that jazz.
Yep, we have all the Li-ion batteries that are required.
Perfect.
All right, you want to go to avionics?
Yeah. So we'll swap over to avionics bay.
the thing on there, I like
You
it.
want to grab the stack? Where's that?
The stack
Yeah.
is right there. Yeah.
Okay. Can you film for me?
Yeah, I got you.
And is this pinned?
This is you want to put it again? Yeah.
Here, oh. Start video. There we go.
Okay, there we go. So here we have our upper body tube section. The cute little nose compressor. But new thing that we're doing this year is we have the same fiberglass nose cone and fiberglass upper body tube, but we're actually doing an aluminum tip this year. So this aluminum tip,
Yeah, sounds
the aluminum tip has a 3/8 by 16 threaded hole that goes up to about here. That corresponds to a thread rod that goes till about here. And then you have a aluminum bulkhead right here that is tightened on. So this entire thing is being held on by compression. In addition to that, it was Loctited and epoxied so that nothing can come apart in flight. So now this
Great.
is kind of part in there. On the interior surface, we have kind of the same situation going on with the two rails. Those two rails are going to be holding our avionics stack, which I'll show in just a second. You can also see in there, I'll quickly mention, two wires that are hanging from sticky antennas that are actually stuck inside the nose cone section right here. So those two sticky antennas correspond to EPRS.
Let Dario.
900
Yeah.
megahertz.
900 megahertz. Anyway, I'll talk about the structure of this thing real quick before I transition to the avionics part of it. But yeah, we have 5 independent fiberglass plates that are holding both our 3 SRAD boards as well as on the other side our COTS systems. So we have a MissileWorks T3 as well as a Perfect Flight CF Stratologger. We have that compliant battery as well, and we have all of our switches. So our switches this year are, I'll let you talk about switches before I go into that. I was just going to show off the mounting structure to make sure that everything's safe and sound right there.
It's the exact same rail system as Halo.
Yeah, that looks nice.
Okay.
And all your electronics are okay being mounted flat
Mhm.
that way.
No
Okay.
orientation dependence built into them.
You want to put this down and you can point and stuff.
I think it might just better to show up here.
All right, well, it's on camera.
Avionics wise, I'll be very brief about how it basically works. We have our COTS flight computer is right there. It's going to be a Stratologger CF from Perfect Flight. We've been using the same board for about 3 years now. So this one's
Yeah, those are great when you can get them.
They're fantastic. They're my favorite. Our COTS GPS system is, as Arnav mentioned, a MissileWorks T3, which we also used last year and worked successfully. So why not use it again? And our SRAD system this year, we went from 1 PCB to we have a design where we have 3 different boards that are all acting together. So flight computer, in general summary, the middle one is our power board, which collects there's our lithium ion battery. That is going to distribute power to the 2 other boards. The bottom one is going to be the conventional flight computer or sensors board. That is going to send the outputs out into the DIN connector that we mentioned here. And this goes out towards the recovery system. And this is going to have the pyro channels and everything needed. And the top board, all the data is going to be sent up through CAN bus, and it's going to transmit all of it on here. We have an APRS radio, so MCC can use that and help track our rocket. And we also have a 900 megahertz radio for our purposes to connect. We have a custom ground station that we have all this data relaying to live, and all that stuff.
Is your SRAD computer, is that controlling deployment?
Yes, both of them are going to do deployment.
It's primary and secondary.
Primary and secondary, yeah.
Okay, so SRAD is one and the COTS is the other.
Yes.
Gotcha. Okay.
Yeah.
Talk to me about the switches.
Yeah, the switches are, I mean, they're nothing crazy. We switched last year from a kind of switch like this one that you can see right there, which we realized that we had some issues with during vibrations in flight, to one that we would have no issues with vibrations in flight, to a barrel jack switch, such that if I just simply pull this out, it locks in that on mechanism with the removal of our flight tag, and it just keeps it on. So it's just a recessed barrel jack switch.
Okay, and it's got a locking mechanism in this, so there's no concern with vibration or G-forces or anything like that.
Exactly why we switched to these, to avoid that.
Perfect.
Any other questions about avionics or?
Nope.
I want to quickly mention one thing about the inner plate connectors. because we had such bad luck with friction fit connectors last year, we actually have all these being snap joints, so it's not gonna vibrate out in flight.
Good.
I think that's true of all connectors on board here.
All right, propulsion next or
Sure.
all right, Scooter.
Sure. So what we did differently this year is we went with a bolted pressure retention system. So instead of a snap ring, we have 8 high-strength steel set screws on the top, so it can slide into the fin can, and on the bottom, it's hex bolts. We have a max pressure of I think 834 psi, and we hydrostatically tested to about 1200 psi and was perfectly fine. We've also already test fired our flight mix, so we have like we know that the casing works. For actual motor retention, it's a 3/8
Give it
inch
a-
steel rod. Yeah, do we have?
Yeah. Here. Yeah, one sec. There we go.
That threads into the forward closure and then threads into the top thrust bulkhead of the fin can. Then we have a secondary retention where our thrust transfer of a snap ring on the outside, and then tertiary retention is the bow tail. So the casing is like outer diameter of the casing is smaller than the end of the bow tail.
Okay. And just a standard bait screen sort of configuration, or?
So it's 4 bait screens. The top one is actually a smaller diameter than the rest of the bottom 3. That's just to allow for more impulse, but keep the corrosive burning down.
Core diameter smaller?
Yeah, like the
Okay, yeah.
it's just it goes from 1.5 to 1.75 inches in core diameter.
Gotcha.
And then the nozzle itself is just machined graphite, 2 O-rings to seal pressure, throat diameter of I think 0.85 inches.
Cool.
That's any questions?
Let's see, got your screw. No, I mean, that's pretty straightforward setup there. What's the wall thickness on your motor tube?
I think it's 0.2 or 200 thou.
Okay. And then your groove holding the snap ring still gives you plenty of,
Yeah. I
Great.
think the groove is down to 0.18 or
Okay.
0.6 or something like that.
yeah. And like you said, you guys are static tested and
Yeah,
all
we
that kind of
just
stuff.
started, but yeah.
Yeah. Great. Cool.
Yeah. Thank you.
All right, anything else?
Let me scan over the checklist really quick. You guys are using shear pins?
Yep.
Yep.
We've been under 9.
And then your nose cone, you just had the antennas in there, right?
Yeah, that's correct.
Deployment, covered everything. Yeah. And I think we have covered everything that we're supposed to.
All right,
Cool.
sounds good. I had a quick question. So yeah, is it just like the same kind of procedure as last year for like the competition? We're doing safety review on registration day into like flight readiness out there. Is that
That's my understanding. Yeah.
all right, sounds good. All right, cool. And then did you want I forget if you wanted do you know if you guys want everything like integrated together when we come for safety, or do you want everything like separate?
I mean, at the same,
Well, no energetics, obviously. Yeah.
well, yeah, no energetics.
Fair enough.
Yeah, you're not going to have everything like shear pin together and that kind of thing, but you basically want to go in there with your rocket and they'll want to see how everything connects and attaches together and all that kind of stuff. So
Sounds good.
cool. All right. Well, good talking to you guys. And yeah, make sure you guys are supposed to need to submit the link to the recording along with all this stuff. And I've got my checklist and stuff here, but I think we're good to go.
I'll do that right after this is done. Yeah, sounds good.
Perfect. All right. Thanks, guys.
Thank you.
Have a good weekend.
Well, you too.
Here's